Okay folks, we have come to the exciting part, another exciting part of our journey into geometric reasoning and geometry as a whole. And this is the point where we've reached the geometric habits of mind. Our discussion is going to primarily focus on the work of Mark Driscoll around this issue of geometric habits of mind. But if you go onto Google Scholar, for instance, and you look, just type in geometric habits of mind, there might be other frameworks that we're not looking at that can add to your professional knowledge as a teacher and as a prospective teacher in this area. It is huge. It's a very difficult section on our paper. We believe it's a difficult section on our paper. It shouldn't be. If we approach it correctly and from the right perspective, we should be able to help learners become better at reasoning geometrically. So let's talk about what I just said. What does it mean to think geometrically? Well, if I put my mind to it, what is geometry in my mind? Geometry for me is a way to organize the space that I'm working in, whether that space be in a figure, whether it be in three-dimensional space, doesn't matter. So how do I organize that? Well, I look at the relational features. So I need to understand, to be a good geometer, I need to understand geometry relationally. To be a good interior designer, I need to understand more than just the space. I need to understand aesthetics and how a person perceives things that are placed in a particular position in a room. At the end of a passage, something works better than what it works on a table, or just being put somewhere randomly in the space. So what does it mean to think geometrically for me is, it means I need to think relationally. Because what does geometry do that we study at school level? It takes relationships, it puts them in place, and based on those relationships, it activates a particular conclusion in our heads. So to think geometrically for me, it is key to be able to think relationally. Why is geometric thought of as difficult? Well, from my perspective, exactly because of that. We do not focus on the relational features enough. There's a certain way to teach geometry. It's called the conditional approach. If these conditions are put in place, in other words, if relationships are fixed in a figure, what can I conclude from that? And if a child or a student of geometry cannot see the relational, they have a huge problem to conclude anything based on that specific set of relationships that should be in place. So that's just my idea about those two things, and why is it thought of it as difficult, and what does it mean to think geometrically? Well, let's talk about where this is in schools. Teachers modeling correct use of terminology is essential. We've seen that through the Van Hille levels of geometric reasoning. We've seen it through the phases of learning. It is still very important. But often we as teachers present a definition to our students rather than letting them explore the conditions and the relationships that leads up to the necessity to define an object or a new object that we're learning about. Well, what does textbooks do? Textbooks focus on the integration phase, in other words, the summary of knowledge. And many teachers start instructing with revealing what learners should find or discover through exploration and personal activity. So that is the issue of we start with a definition and then we apply. We start with teaching the theorem and then we apply. We're turning everything the wrong way around. I wrote a textbook, and one of the comments about my textbook was that it's very wordy, it's too wordy. And my response was, yes, it is wordy, because I'm trying to unpack the relationships, the relational understanding that's necessary to deal with the object that we're learning about. Okay, so folks, that's what happens in schools. Activities are tiered, so students first have exposure to shapes, beginning sorting them visually, and then talking about the properties that they see. We need to be as teachers, be very aware of what the Van Hillers have argued in their research, and what we're going to learn today in terms of geometric habits of mind. Take that into the classroom and into our practice to activate the type of thinking that we know is necessary for learners to have in order to function more or less at the level that Euclid did. So as students progress, geometry becomes more and more abstract. Now that is what happens in schooling today. If you do a curriculum map about geometry and geometric learning, just at a secondary level, from grade 8 to grade 12, you will see how little complexity we have at the lower grades. And then all of a sudden, when we in the further education and training phase, grade 10, 11 and 12, the knowledge compounds into more complex ideas and more abstract ideas about geometry. Well, research indicates that students, and we've spoke about this often, enter high school level at level 0 and level 1. Thus they have great difficulty with formulating proofs. They have difficulty even with formal proofs, and thus solving riders, which relies on this expert relational understanding of the geometric theorem and the geometric proof. And then they battle with geometry. Definitions progress to only contain necessary information. That is the purpose of a definition, the minimum and sufficient to define what relationships, what properties are minimum and sufficient to define the object of learning. Now, if we start with the object of learning's definition, we are saying that property, this property, this property is necessary. Remember that. It's not creating the flexible and the relational knowledge that we want to create when we talk to learners in a mathematics classroom. Okay, so we're focusing on habits of mind today. So let's quickly, before we start with the work, talk about why are habits of mind important in mathematics and in the mathematics classroom. Well, firstly, they help us understand established results. They don't help us remember established results. That's the word that is not there. It's often very necessary to see what a statement says and what a statement does not say. That is saying it helps us understand established results. That is what habits of mind are designed to do, to create understanding, and through that understanding develop flexible knowledge and relational knowledge that can flexibly be applied within the subject discipline, within the particular content that we're learning, and also across subject disciplines. I was teaching at a high school, Norcombe Park High once, and the science teacher came down to me. It was just at the beginning of my teaching, and said to me, "Did you teach the children the sine, cosine and area rule?" I said, "Yeah, we just finished it." No, we actually, we did finish it. And the teacher said to me, but they can't apply it when they work with vector diagrams in physical science. Is it possible for you to do it earlier in the year so that they get more experience with it and then apply it across the context? Well, if I think about that statement today, it was because at that early stage in my career, I did not teach relational understanding. I did not even know that existed. I taught what the textbook told me to teach. And it was clear to me after that discussion that the knowledge, thinking back on it today, the knowledge wasn't flexible. The knowledge wasn't relational. It was how to do, not understanding why that result applies. The second big thing about habits of mind, and this is most probably the key issue behind it, is it develops productive ways of thinking. You saw in a previous video where we discussed the results of a geometric activity. I spoke about get the habit of putting corresponding angles that are equal in that order, so you can use that which you've just written to read off the corresponding sides and the relationships in the diagram. I've also spoken about creating a habit of, once you've calculated an answer, put it on the diagram so that you know it's there. I've often done workshops with learners where I've done geometry with them and they want to preserve the diagrams and not make a single mark on it. So what they would often start doing is make a whole list of things that are equal in the diagram. There's no connection there. That's a very bad habit, because now you've got to go and search for a connection. Okay, and that connection is not relational. It's just because there's a SA there as a side. I'm looking for another SA in my little shopping list so I can see if I can use it. No. Okay, so that's not developing a productive way of thinking. So habits of mind are things that are streamlined and polished and works effectively to help us understand and work flexibly with results. Okay, let's move into the work of Driscoll. That book is a little bit expensive. It's pricey if you buy it online, but folks, trust me, it is worth the money you are going to spend if you buy Driscoll's book. And trust me, I do not get royalties or payment from Mark Driscoll, but I can recommend this book. I can highly recommend this book to you for purchase. Driscoll's Geometric Habits of Mind. The first habit is seeking relationships. And we're going to work through all the habits. There's 4 of them. Seeking relationships happens in diagrams, across shapes, across properties of shapes. We'll talk about that in depth. Then checking the effects of transformation. A big idea in mathematics is what remains invariant, what changes and what does not change if I change the properties or the order of properties in a shape. That is a habit of mind. It develops, by the way, if I can say it at this point, it develops the relational understanding. The next habit of mind is generalizing geometric ideas. Is this always going to be the case? If those relational features are in place, will this always be the conclusion? If I change the shape a bit, does the conclusion remain the same? And then last, but I think the most important one, is balancing exploration with deduction. How much exploration is needed before I can actually deduce a property about a geometric shape? So let's start with seeking relationships. What is it about? It's about actively looking for relationships within and between geometric figures in 1, 2, or 3 dimensions. Thinking about how the relationships can help you understand and solve problems. And I want to add a word there. The relationships can help you understand relationally and solve problems. Folks, these habits of mind will help a child understand geometry at a level that you want them to understand it. Why? The first habit, they're seeking relationships, relational thinking, in a diagram, across diagrams, in a class of shape, across classes of shapes. We're looking for relationships. Relationships can be between or among figures, between or among whole figures and their parts, between or among concepts that we deal with in the class. What is the relationship between congruency and similarity? What is the relationship in grade 12 between the proportionality theorem, which works with the line that is parallel across a triangle, dividing the sides proportionally, and the similarity theorems that follow after that? What's the relationship between those two theorems and the tangent-secant theorem? What does the tangent-secant theorem do that the tan-chord doesn't do? There's a lot of questions that is asked when seeking relationships. We look at what relationships are in place, what the implication is with that collection of relationships that are in place. We deliberately seek those relationships. There's an example, which you've got 4 figures there, and before you tell me, oh, those are rectangles, think very carefully about, are they rectangles? Because remember, a rectangle, there's nothing here that tells us that they're rectangles. So don't think at van Hille level naughty and think, that's a rectangle. Just an idea to remind you. I want you to pause the video at this point to think about the relationships that are put in place in those diagrams, and then, well, let's have a look at your reasoning and what it is that you look for. The big question we're asking is, which two make the best pair amongst those 3 figures? And just to focus our thinking, I'm going to say, let us say they are rectangles. The diagram does not indicate it. The diagram only indicates pairs of opposite sides that are equal. So it could be a parallelogram or a rectangle, or those figures where those properties are true. Pause the videos and try and answer that question. Okay, I think let us go out of here and let's go to my hovercam and see what it is that you focused on when you looked for the relationships. Now remember, let me just get rid of this banner. There's quite a few things that we can focus on. But let's just start somewhere. Let us look at, we're trying to answer the figure which two best suit each other, which figures best belong together. So let us look at area first. Area here is 60 units squared. The area there is 15 units squared, and the area here is 8 units squared. Well, if I look at area as an organizing principle for my investigation, then these two fit nicely, because this one is 4 times the area of this figure. This one I'm going to have a problem with, because it's going to be a fractional component. So this is a straightforward, that the area of this is 4 times that area. Look at the perimeter. If I work with the perimeter of the first figure, I get 20 plus 12, it's 32 units. If I look at the perimeter of the second figure, I get 10, which is 16. And look at this. This perimeter is twice that smaller perimeter. So there's a direct relationship here. But now look at the third one. The perimeter here is 10 units. Again, okay, so I can look at the relationship between area and perimeter in each diagram within the shape, and then establish the relationships across the shape. Plural. Here, this is double that. The side length here is double that side length, which is not the case here, which is not the case here. But if I look at the relationship in those side lengths, I can see that this relationship as between this side and that side is the same as the relationship between this side and that side. So if that becomes the principle I'm looking for, then these two figures are best suited. The sides are in a relationship of 6 to 10, which simplifies as 3 to 5. The same here. The sides are in relationship 3 to 5. So based on perimeter, based on area, based on side lengths, it would look like this shape. These two shapes are the best ones that fit together. Now I know most of you most probably only looked at the side lengths and looked for that proportion, but why I wanted us to do this is to show that there is more to look for when we seek for those type of relationships. So let's go back to our slide presentation. Okay, so what were the questions that we were asking ourselves when we were looking at the differences? How are these figures alike? In how many ways are they alike? How are these figures different? What would I have to do to this object to make it behave like that object? Okay, and if I look at the two figures here, I think it was our last point that we were looking at, is if we double these sides, we get that over there. We get those two sides that are lying in the bigger shape. So the point of this is, what relationships do I feature on? What do I need to look at that are important in those relationships across figures and within a particular figure? Okay, let's move to the next habit of mind. Checking the effects of transformations. That ushers in the big idea in geometric thinking, and that is variance and invariance. Analyzing which attributes of a figure remain invariant and which change when the figure is transformed in some way. Okay? Attributes of the figure that may be affected by transformations can include orientation, its location, area, perimeter, and volume, if the volume exists in a 3D space, that exists, the side lengths, the ratio of those side lengths, the angles in the figure. If we go back to the previous slide, if these were rectangles, all these figures belonged together, because all of them would have had, on the basis of right angles, would have had right angles. Okay, so what does it mean to talk about invariance? It's a relationship that is not changed by a designated mathematical operation, such as transformation of coordinates. If you're working in software, dragging a point changes the way that relationships are being put together. Okay, so always checking the effects of transformations on figures is a big habit of mine. What do I need to change here to make those two angles in the figure the same? What do I need to change in a rhombus to make it a square? What do I change in a parallelogram to make it a rectangle, or in a rectangle to make it a parallelogram? Is a rectangle always a parallelogram? Is a parallelogram always a rectangle? Okay, so what changes from one shape to the next? Here's a nice example. A square's diagonals always intersect at right angles. So there's always a right angle there. The question is that true for a rhombus? Now let's talk about that. What is the same in a rhombus that is the same in a square? Okay, and that is that all the sides have an equal length. Now if that is the case, if all the sides have an equal length, then I want to know, I don't change the length. That's the property that remains invariant. The property that's going to change is how those lengths are placed in relation to one another. So the question is this going to be true for a rhombus? Now, I want you to think about that for a while. I'm going to just pause the video and think about that and come back and let's discuss. Well, we've triggered the thinking. What properties remain invariant between a square and a rhombus? Square, all four sides are equal. A rhombus, all four sides are equal. We didn't speak of any other property. Now let's see. There's my square, assuming that's my square. Internal questions that I can ask myself is, what changes? Why does it change? Okay? What stays the same? And why does it stay the same? So if I have constructed this on a diagram, then I can push it aside, and that forms the rhombus. Push it flat, drag a point. Then drag it even more. Well, it looks like that those relationships remain invariant. The fact that the diagonals are indeed intersecting at a right angle. They are orthogonal, the diagonals, in a square and in the rhombus. Okay, now why is that the case? What properties remain invariant? What changed? What was the transformation I made to this figure, and why did those properties remain invariant? Is a big habit of mine. Now, folks, you really have to know your constructions and your software to be able to construct a square from scratch in Sketchpad. Okay, but you can just think about the idea of equidistance. Equidistance, immediately concept image, circles. So you can work with intersecting circles to construct a square. There's many ways you can construct a square in software. But software, the fact that you can use software to illustrate this quite nicely is big. Okay, so that concludes the checking of transformations. We're moving to generalizing geometric ideas. So we've now dragged that rhombus around the circle, did what we want to, and we told the software to measure the angle, and we saw, okay, but that's always the case. So now we want to understand the always and the every. Why is it always the same? Why is every diagram that I dragged a point of, the diagonals remained perpendicular? Okay, so here we're interested in the always and every related to the geometric concept and procedures that we are dealing with at this point. Generalizing progresses through two stages here, folks. This is the part, and if you can also get hold of his book on algebraic reasoning, you will see that one of the habits he talks about there is generalizing, how important it is to for a child to be afforded the opportunity to generalize. Okay, and for us to actually generalize. That's what mathematics is. It's the generalization of relationships. That's what mathematics does. And it does so in geometry as well. Okay, so we're saying, or Driscoll argues that generalization progresses through stages. Conjecturing about the always and the every. So you look at this and you make a choice. Oh yes, it looks like it always is going to be the same. So I'm going to expect that it is. And then we test that conjecture. So we conjecture through exploration. We test the conjecture. We draw a conclusion about the conjecture. Okay, and then we make a convincing argument about our conjecture always being true. And that argument formalizes itself in a proof, in the form of a proof. Okay, so let's look at the generalizing geometric ideas in action. Connecting the midpoints of a quadrilateral creates a parallelogram. Okay, if we did that with that particular quadrilateral, it created a parallelogram. what other quadrilaterals will this work for? Now folks, notice the important thing here is this is a random quadrilateral. It's not a parallelogram within which we're going to draw another parallelogram. It's not a regular figure. It is any quadrilateral. Now obviously this with software would work beautifully. To construct a quadrilateral, measure where the midpoints are, join them, and then how do we find the sufficient and necessary properties? Well, let's look at the pairs of opposite sides, look at the one pair's length and gradient. And if it doesn't change, the figure remains a parallelogram. Okay, so you can see now how the relational interacts quite nicely with our actions when we use geometric software to investigate and to support these habits of mind. Okay, generalizing geometric ideas, internal questions. Does this happen in every case? Would this happen? Why would this happen in every case if it appears that it does happen? Have I found all the ones that fit the description? Well, what is the description here? I need a quadrilateral, I need its midpoints, I need to join the midpoints. 3 relationships in place. Conclusion is the figure formed by joining those midpoints is a parallelogram. Okay, so does this happen in every case? We've looked by dragging the quadrilateral around, by changing its orientation. Why would this happen in every case? Well, we need to think about that. That helps you, the why part helps you thinking of the relational features needed to prove this. Have I found all the ones that fit that description? Can I think of examples where this is not true? And if I can think of them, do I need to revise my generalization? Would this apply in other dimensions? So would this apply if I worked on a 3D shape, where I worked with the midpoint of each of the sides? Does it then construct a regular 3D shape beyond what I'm looking at the moment in the particular figure? Okay, so does it transfer from a plane to 3D space? Okay, folks, very important, very, very important. You must afford learners the opportunity to go through these processes, activating these habits of mind. There's a flatter one that I drew, and it seems, vanilla level naught, it seems like it still remains the same. It's okay. I'm at the rigor level now, but I'm looking at the picture and I said, it looks the same. That's a vanilla naught statement. Now I'm trying to put the building blocks in place to prove that it is the same. And that process I need to manage very carefully. Brings us to the next habit of mind. Balancing exploration with deduction. I explore a bit, I deduce or I conjecture something. I see that that's always the case. I explore a bit more and I balance it with decision making. Okay, that habit of mind is an iterative and a cumulative process that alternates between a few things. Now just the word iterative, if you don't know what iterative means, iterative process is one that you repeat again and again, using the results from the previous stage. And cumulative, becoming successively larger, stronger, and more effective. Now you've heard me refer to cumulative knowledge building in the videos. That means my knowledge is not pigeonholed. My knowledge is built and made more complex, until the whole is fitting into a beautiful relational space and can be applied flexibly. So, balancing exploration with deduction is iterative and cumulative process. It alternates between exploring, in other words, structured by one or more explicit limitation or restriction, and then taking stock of what is being learned through that exploration. In the case of the midpoint midpoint, there is a wider body of knowledge that takes polygons that are irregular, joins their midpoints. Folks, do that. Do it to a triangle, a square, a pentagon, a hexagon, a heptagon, an octagon. Carry on. See what happens. It is fascinating. The polygon midpoint theorems is a whole string of theorems and stuff that you can work with. It's fascinating to see. We're only looking at the quadrilateral. Okay, so we explore and we take stock in our exploration. What is it that I changed, and what does the figure show me? Does my conjecture still hold that I made earlier? And then trying various ways to approach a problem, and regular stepping back and looking and taking stock of the object that you're working with. Okay, here's a nice one. Is it possible to draw a quadrilateral that has exactly 2 right angles and no parallel lines? Pause the video. Draw one. A quadrilateral has 2 right angles and no parallel lines. Pause the video. We'll come back. Well, whenever I do this activity in class, it usually takes about 5 to 6 minutes for students to actually see that this is possible. But in the beginning, the first 3 or 4 minutes, they also know it's not possible, no, it's not possible. And I look at them and I say, well, look again. Try something else. Orientate things differently. See what you find. Okay, so what are the internal questions? There's the figure. It's a kite. Okay, or it doesn't have to be a kite, but that looks like a kite, van hele level naught. So it's a figure where the sides are not parallel. And the issue of parallel most probably interfered in the stuff that you were drawing. But if you take 2 right angles, you orientate them so that the 2 right angled sides intersect. You've done what you should have done, having read this paragraph, or the conditions that we want to put in place. Okay, so internal questions. How can my earlier attempts to solve the problem inform my approach now? What happens if? Well, if I drag a point, if I constructed this, or I drew it differently, what did the action tell me? So what happens if I draw the lines differently? What did that action tell me? How can earlier attempts to solve the problem inform a different approach? Okay, that's habit 4, folks. Balancing exploration with deduction. Another nice activity here is the folding activity. Take a sheet of paper. Make any fold in that sheet of paper. Then make another fold so that the sides line up. What can you say about the angle that is formed? Now, it's quite a lot of words there, so let us do this under the hover cam and see what it is that we mean. I'm just going to use this paper. We're going to do any fold. We're folding it like that, and then it says fold it again so that those two sides lie on top of one another. And what is it that we've just formed? Well, van hele level naught, it looks like a right angle. Now the question is, well, is it? What relationships are in place there that you've put in place that made it a right angle, and how can I prove it? Okay, so we made a conjecture, and we now, well, you can prove it by opening the paper and looking at relationship, or what it is that you did. And with every fold that you made, what new property did you create, and how the accumulation of those properties brings you to conclude that it's a right angle. Okay, folks, this is a very important video. I will suggest that you watch it again slowly and think about what it is that we do as teachers in the geometry class. Just a reminder, the relationship, the habits of minds, habits of mind that Driscoll talks about. First of all, seeking relationships. Those relationships are within a figure or across classes of figures. Checking transformations and their effects on the figure that I'm working with, or the classes of figures that I'm working with. How does those transformations change the shape? What remains invariant and what changes? And from that exploration, we move to generalizing geometric ideas. We ask the questions: will this always be true? Why is it then always true? What relationship cements this conclusion? And then, very, very big, the balancing of exploration with deduction. How do I use that in the mathematics classroom? How much exploration is necessary before I can make a deduction of the thing that I'm trying to establish, the rule or the figure that I'm working with? Okay, folks, I hope that helped you to build a better understanding of what it means when we teach geometry, how to teach it, what methods to apply in the geometry classroom. If you've learned something, please like the video, subscribe to the channel, share it, and feel free to comment in the space below.